Well, hello and welcome again to our journey into linear algebra, and we've been looking at rotations in the plane in 2 dimensions and isometries in general in the plane. We're going to now move to 3 dimensions and look at rotations in 3-dimensional space. Now, you need to think a little bit about the geometry here. So to specify a rotation in R cubed, we need to give the axis of rotation that we're rotating about, and that will be unaltered by the rotation, and we need to give the angle of rotation, that is the angle through which a vector perpendicular to the axis is rotated. So we'll let v1 be this the vector that is the axis of rotation. So we have a vector v1 up here, which is our axis of rotation, and we can then take an orthonormal basis containing v1 using the vectors v2 and v3, and so we can take an orthonormal basis for R cubed containing this v1, and then if we draw a diagram, we can see then that the any vector that's in the plane down here, the plane spanned by v1 and v2, sorry, v2 and v3, then that'll be rotated in this plane through an angle alpha. So with respect to this basis v1, v2, v1 doesn't move at all, so any vector on v1 is not going to move at all, so it has the image of that under this rotation will have coordinates 1, 0, 0. And then we're back now in the plane here with respect to these 2 basis vectors, and so we're simply going to rotate a unit vector along this axis through an angle alpha, a unit vector along this axis through an angle alpha, and we've seen before that that's what happens to it, and so they're the coordinates of the images of those 2 unit vectors in these directions. So R alpha then is this matrix with respect to this basis v1, v2, v3. It's the matrix of this transformation. Now, as in the 2-dimensional case, this R alpha is an orthogonal matrix. You can check that easily, and you can check its determinant is clearly 1. And the trace of this matrix is a little bit different from before. We now have 1 plus 2 cos alpha for the trace of the matrix. So, with respect to this basis, given R alpha, we can use this to find the angle alpha up to sine. We'll talk about the sine a little bit later. So again, the inverse of this matrix, we're just going to rotate through an angle of minus alpha, so we can write that down. And as before, we can do the same calculations we did before and show that the eigenvalues and eigenvectors of this matrix are lambda equals 1 and v is 1, 0, 0. That's the v1 vector that we started with respect to this basis, and the other 2 eigenvalues are complex, and they're the corresponding eigenvectors. Now that's fine if you've got the axis v1. What happens if we take any rotation matrix, any rotation in R cubed, then we've seen how to find its matrix with respect to a carefully chosen basis, and hence by a change of basis with respect to the standard basis. So if on the other hand we're just given a 3 by 3 matrix, we'd like to be able to tell whether it's a rotation matrix, if so what's the axis and angle of rotation, and the following theorem gives us the answer to these questions, which is very nice. It completely categorizes these things. So if Q is a 3 by 3 orthogonal matrix, and it's got determinant 1, so you've got a 3 by 3 orthogonal matrix with determinant 1, then Q is a matrix of rotation in R cubed. Now I'm not going to prove this here. You need to look at some textbooks on this to get a detailed proof of this. If V is an eigenvector for this matrix Q corresponding to lambda equals 1, then that's going to give me the axis of rotation, because then QV will just equal V, so it won't move, and the axis of rotation then is just given by the line x equals mu V, where mu is a real number. Now to get the angle of rotation, well, we simply take the trace of this matrix Q, and that will be the trace of the rotation matrix, which we saw before was 1 plus 2 cos alpha. And from this formula, we can at least determine alpha up to sine, up to plus or minus. And we'll have a look at that question a little bit later. It's a little bit more difficult to determine exactly what the sign of the angle, whether it's positive or negative. So a couple of examples to work through here. And so I've got this matrix Q, here it is. And we want to explain why Q is a rotation matrix. We want to find the axis of rotation, and we want to show that the angle of rotation is plus or minus pi on 3. At this stage, we'll come back and look at determining the sign of this a little bit later on. So here's the worked solution to this. So here's our matrix Q, 1/3 times this matrix. I'll leave you to check that Q transpose Q is the identity. You can see if you take the dot product of, say, this column with this column, you'll get 2 plus 2 is 4 minus 4, 0. You can dot product this with this, you get 0. You dot product that with that, you get 0. If you take the length of any of these vectors, you're going to get 4, 8, 9, you get 3, divided by 3 is 1. So you can either do this calculation, or you can just observe that the columns of the matrix are of unit length and they're all mutually perpendicular, which is sufficient to show that Q is orthogonal. So to get the determinant, I've just done one example of how to calculate the determinant of this thing here. Now we've got to be careful with when you've got factors out the front. This 1/3 is going to be affecting each of the rows. So when you take it out of the determinant, you've got to take the 1/3 out 3 times, and so you get 1 on 27. And all I've done here is I've just done a little bit of row reduction. I've just replaced this row with the sum of these two, and I've done this one minus a half of this one, which gives me this here. And then we can just expand down the first column for the determinant. So we get 1 on 27 times 2 times 9 plus 9 halves. And when the dust settles on that, you get 1. So that tells me Q is a rotation matrix. So they're the two conditions. We have to check it's orthogonal, determinant 1. So this is a matrix that will rotate in space. To get the angle of rotation, we go for the trace. Now the trace of the original matrix is 2, 4, 6 over 3 is 2. So the trace of Q is 2, and our formula from before tells me that this is the same as 1 plus 2 cos alpha, where alpha is the angle of rotation. We can solve this to get cos alpha is a half, and then alpha is plus or minus pi on 3. At this stage, we're not too sure which sign is correct. Not sure which of the two is correct at this stage. We'll come back and have a look at that later. To get the axis of rotation, we want the eigenvector corresponding to lambda equals 1. That is, we want the vector that Q doesn't change. So this vector doesn't get moved under this rotation, so it's the axis of rotation. And that's the same as saying B belongs to the kernel of Q minus I. That's how we find our eigenvectors. So now just a little bit of note on the arithmetic here. This third out the front always causes grief. So coming back to the matrix here, we're going to be subtracting this minus I. So with the third there, we can leave the third there and subtract 3 times I, or 1/3 of 3 times I. And physically that simply means we're going to be subtracting 3 off the main diagonal of this if we keep the fraction out the front. So I subtract 3 off the main diagonal in the calculation of this matrix down here, and that's all I've done. And, well, various ways I could do some row reduction on this. I just noticed that minus 1, 1, 1 looks like it'll work. That is, if you take minus 1 of these, so that's 1 plus 1 minus 2 is 0, and then 2 minus 1 is 0, and then 1 sorry, minus 1 is minus 2 plus 2 is 0. So you can do it by inspection, or you could do one little row reduction on this and show this was the eigenvector. This was the vector in the kernel of this matrix. So the axis of rotation then is x is t times minus 1, 1, where t is a real number. Now, as a second example of this, I always like to do a couple of examples. So here is another example of this. So Q is 1 over 11 times this interesting looking matrix. And again, we want to show this is a rotation matrix. Find the axis and angle of rotation. So there's our matrix. We do the same thing again. We observe that if you dot product any of these together, you get 0. And the length of each of these vectors is 11. Matrix is nicely chosen to avoid fractions and irrational numbers. There's an art to constructing these things, but here's a nice matrix with the right properties. So you can work out Q transpose Q as I, so it's orthogonal. And again, I've just quickly worked out the determinant here. You have to take out 1 on 11 cubed. And I've just done one row reduction because this 9's not very nice here, so I've just replaced the second row with the second row plus 3 times the first. So 3, the 2's are 6, minus 6, 0, 6 3's are 18, minus 7's 11, and so on. Now I took an 11 out of this row here, so it now becomes 1 on 11 squared, and then I've just expanded down the first column. So I get 2 into this subdeterminant. Remember, I've taken 11 out, so it's 1, 3, minus 6, 2. And then minus 0 times I don't care, then plus 9 times. You cross out the row and column, so we get this subdeterminant. And I've taken the 11 out, so we get 6, 9, 1, 3. And then I just worked out the determinant, and it comes out to be 1. So that tells me then, therefore, so Q is a rotation matrix. Now to get the angle, again we take the trace of Q, go back to Q here, the trace is going to be 4, that's minus 3 on 11, and that's 1 plus 2 cos alpha, and I can simplify this, so this gives me, I hope, take minus 1 on this side, that gives me minus 14 on 11 divided by 2 is minus 7 on 11. Now again, we're probably best to leave it in this form, and this doesn't pin the angle down. There are two possibilities here. The cosine is negative, so it's either in the second or the third quadrant. Now for the for this one here, the QV is equal to V. Again, we're looking for the axis of rotation, so we want a vector in the kernel of Q minus I. And again, this time we're going to be subtracting 11 off the main diagonal if I want to keep that 1 on 11 out the front, which produces this matrix. And if you stare at that, you can do some row reductions, but if you just notice here, you've got minus 9, 9, minus 6, 6, 9, minus 9. So if I just take the first plus the last, kill the middle one, that will do to the kernel. This matrix, of course, has rank 2, nullity 1, so there's only one eigenvector hiding in the kernel here. So the axis of rotation then is x is t times 1, 0, 1, where t is real. Well, that answers most of the questions about this, except the problem of finding the sine. And I'll just say something about this here without giving too much in the way of proof. But there's a little procedure that determines the sine of the angle alpha. So what we do is we start off, we take the axis of the rotation, which we've worked out before, and we take any vector which is perpendicular to this one. We assume that the alpha is between minus pi and pi in this. So to work out the sine of alpha, turns out to be the same as the sign of the determinant of V1, V2 and QV2. Now I'm not going to give a full proof of this, just to give a justification for this. This determinant is measuring the volume, the signed volume of a parallelepiped or a parallelepiped based on these, spanned by these three vectors. So if you start off with one vector V1, you take a perpendicular vector to that V2, and then you rotate that through an angle alpha. We're not sure whether it's positive or negative. Then we're going to end up with three linearly independent vectors, and the volume, the signed volume of the parallelepiped is going to be this thing, and it depends on whether we had a positive or negative orientation of the angle as to whether we get a positive or negative, inverted commas, signed volume. So if this is negative, then it must have meant that we rotated through a negative angle, and we don't have a right-hand system of vectors. So that's just a vague explanation of why this method works. So in this example here, to work out the angle, so going back to my earlier example that we had here, which was this 1/3 here, we found the angle of rotation was either pi on 3 or minus pi on 3, and we found that the axis was spanned by this vector. That was the vector that spanned the axis of rotation. So I take a second vector perpendicular to this one, so I may as well just take 1, 1, a dot product to give me 0. I work out Q times V2, so I multiply this times this one. So I'm just going to be adding these two, so I get 303. That looks good. Finally, we find the determinant of this matrix, V1, V2 and QV2. I did a little bit of elementary row operation, so I've just removed these by Gaussian elimination. So I add these two, I get 0.23, add these two, I get 0.16. Now we can work out the determinant of this. That's minus 1 times this subdeterminant. That's 12 minus 3 is 9, times minus 1 is minus 9. And then we get zeros here, and this is negative. So this tells me that the angle of rotation then was minus pi on 3, not plus pi on 3. And that is the end of the story on the rotations in R cubed. This completely determines then all of the rotations in R cubed.